Welcome to Etabs 2015 Advanced Series. In this tutorial, we will be discussing about the response spectrum analysis. In the beginner's tutorial, we have discussed about the seismic analysis of a G+3 building. The seismic analysis method we adopted there was a linear static method. In the case of a small or a regular building, it is possible to predict the translational mode. So in the case of a linear static method, we only consider a single mode case. But in the case of an irregular or a tall building, it is not possible to predict the seismic behavior of a structure with respect to single mode. In that case, we consider multiple mode cases, which is used for the dynamic analysis. So, the response spectrum method can also be called as a multiple model response spectrum analysis. So here, in our model, we have a total of 2833 joints. As these joints are spring supports, let's consider 2 degrees of freedom for each joint. So, from this model, we can generate a total of 5666 model cases. Let's assume our structure to be a single straight line. So when the seismic acceleration is applied on each joint of the model with respect to single degree of freedom, different mode cases with unique model response are obtained. That is from mode 1 to n number of modes. So the response spectrum analysis, we combine all these model cases to obtain a single response for the structure. The single approximated response is plotted as a smoothed response spectrum where the time period is plotted along the x-axis and the acceleration along the y-axis. So, with respect to this response curve, we are going to perform the dynamic analysis. So here in the load patterns, I have defined the earthquake load along both x and y direction with respect to the American code, that is ASCE 710. So along the x direction, I have assigned the direction and the time period that is corresponding to a reinforced concrete structure, and the factors, I have given the response modification factor as 8, the omega, that is the system overstrength factor, as 3, and the deflection amplification value as 5.5, and the occupancy importance is being given as 1. And under the seismic coefficients, I have given the user defined values for SS and S1, where SS is 1.145 and the S1 is 0.52, and the long period transition period has been given as 8 seconds, and I have defined a site class as D. So along the y direction, I have given the same factors with respect to the seismic load that I assigned along the x direction. So next is we have to define the mass source, which I already defined here. So here the mass source is basically defining the load cases that has to take part in the base shear calculation. So here I have assigned the dead load, the masonry load, and the 25% of the live load. Next, we need to define the model cases. So for that, go to define and select the model cases. So here let's add a new case, and we will keep the name as model 1 itself. And under model case subtype, there are 2 types of method you can opt for, either an eigen or a Ritz method. So here we will go with the eigen method, and under P delta or nonlinear stiffness, we will select the non-iterative based on mass. And here under other parameters, we will select the maximum number of modes for the time being as 12 and the minimum number as 1, and we will keep the rest as it is and click on OK. And after defining the model case, go to define again, and next let's define the response spectrum function. So go to function and select the response spectrum, and here let's add a new function. So here we are defining the response spectrum function with respect to ASCE code. So let's name it as response spectrum. And here I'm going to give the SS and SN values as user specified values. So my SS value is 1.145 and the S1 value is 0.52, and let the long period transition period be 8, and the site class is D, and these are the function points where with respect to each period the acceleration is being plotted. This is from where we obtain our response spectrum curve, and here we are plotting the response spectrum curve with respect to 5% of damping. And after making all the selections over here, click on OK. So we have defined the response spectrum. And before going to next step, I would like to discuss something. There are three methods to combine different model case responses into a response spectrum curve. The first one is the absolute sum method, where the peak response of each model case is summed up together to form a single response curve. But this is very unlikely to happen, as the peak response of each model case will be occurring at different time period. The second one is the square root of sum of squares method, which will give the almost accurate response of the structure. But the main drawback of this method is that it cannot give the correct result if the frequencies are very closely spaced. The third method is a complete quadratic combination, which gives the correct response even if the frequencies are closely spaced. So, for our analysis, we will be adopting the CQC method or the complete quadratic combination method for the model response superposition. After defining the response spectrum function, we need to define that function into a load case. So for that, go to define and select the load cases. So here we need to add our response spectrum function into this box. So click on add new case, and here let it be, we are going to name it as RS, and the load case type is the response spectrum. So select from the drop down, that is response spectrum, and here as default the mass source is also being defined here because we only have defined a single mass source. And here under the loads applied, click on add and click on add again. So here we are going to define the acceleration with the u1, and here we are going to define an acceleration with respect to u2 axis, and here it is already been assigned as a default uniform, but we need to define as response spectrum over here. This is a function that we have defined before. Next is the most important step, that is applying the scale factor for the response spectrum function. So the formula for applying the scale factor is Ig divided by R, where I is the occupancy factor, which is 1 in our case, and G is the acceleration due to gravity, which is being defined here, and R is the response modification factor, which is 8 in our case. So the final scale factor value that is obtained will be 1225.83. So here I am going to change the scale factor obtained for the both acceleration. Here if you select the advanced option, you can specify the angle in which the acceleration is going to act, but for the time being I'm just leaving it. And under other parameters, we will select the model load case, which is model 1 itself, and the model combination method we are going to adopt is CQC, and the directional combination type, let's select the CQC itself, CQC3. And in the case of model damping, we are going to apply 5% of damping, which is already being defined here. So here make sure you select the constant damping for all mods and click on OK and click on OK. So here you have finished assigning the response spectrum into the load case. And now let's analyze our model. The analysis of the model is completed, and after the analysis, the first thing to check is that whether the number of modes considered for the analysis is sufficient or not. According to the American code, the combined model mass of the model cases considered should be at least 90% of the actual mass along both directions. For our current analysis, we have considered 12 number of modes. So to find out whether it is sufficient or not, we need to find the model participating mass ratio. So for that, go to Display, select Show Tables, and here under Analysis, select the results, and here under Model Results, check the second one, that is Model Participating Mass Ratios, and click on OK. So here a table has opened up which is showing the model participating mass ratios with respect to each mode. So we have considered 12 number of modes, and let's go to the 12th mode and see whether it sum up to 90%. So along the x and y direction, in the case of forces, it has sum up to 90% along the x direction, but only up to 88% along y direction. And if we just pan a bit more right, you can see in the case over here, along the x direction it's only up to 73%, and along the y direction it's just 76%, which means that we have to increase the number of modes for our dynamic analysis. So for that, let's unlock the model and reanalyze it again with 50 number of modes. Go to Define and select the model cases again, and let's modify it. So click on Modify. So here under maximum number of modes, let's change the 12 number of modes to 50 number of modes, and click on OK, and let's analyze it again. The analysis is complete, so let's check the model participating ratio again. It's already been checked here, so let's click on OK. And here let's scroll down to the last mode, that is mode number 50. So here under the 50th mode, you can see that the model mass has been sum up to 98% along the x direction and 97% along the y direction. And over here under both directions, you can see the model mass has sum up to more than 90%, which means that the number of modes, that is 50 number of modes, is adequate for considering the dynamic analysis. And next, let's go for the base reaction check. So for that, go to Display, select the Show Tables, and let's uncheck this part again and go to the Reactions and select the base reactions and click on OK. So here you can see the base reactions where we can see Ex and Ey, which is the earthquake load that has been calculated with respect to linear static method, and also we can find the earthquake reactions with respect to response spectrum method. According to the Codal provisions, the Bayesian that has been calculated from response spectrum function must be at least 85% of this calculated static Bayesian, which has been expressed in the form of Ex or Ey. So let's find out whether the response spectrum function satisfies this criteria in our case. So in our case, along x-axis, the ratio of the response spectrum Bayesian with respect to the static Bayesian accounts to only 37.8%, and along y-axis it is almost just 41%. So we need to scale up the response spectrum Bayesian to 85%. So for that, we are going to use this rescaling equation, that is Ig divided by R into 0.85 into static Bayesian divided by response spectrum Bayesian. So here the Ig divided by R is a scale factor that we have already applied in our response spectrum function. So the final value or the new scale factor that we obtain after applying this formula is 2753.25. So we need to input this value as a new scale factor in the load case where we have defined our response spectrum function. So for that, let's unlock this model and reanalyze it again. So go to define and let's go to the load cases where we have defined a response spectrum function, and let's modify the response spectrum. And here this is our old scale factor, and we need to input a new scale factor which is 2753.25. And click on OK and analyze it again. We have finished analyzing our model. So here you can find that the Bayesian value that has been calculated for the response spectrum function has been scaled up along both x and the y-axis. So next we need to find whether the newly scaled up Bayesian value for the response spectrum is sufficient or not for the dynamic analysis. So here we can find that the newly scaled up response spectrum Bayesian value with respect to the static Bayesian accounts up to 85% along x-axis, and along y-axis you can find that it accounts up to 92%, which means that the newly scaled up Bayesian value is sufficient for dynamic analysis or response spectrum analysis here. So here we have finished defining the response spectrum function, and with respect to this Bayesian value you can find the forces, the displacement and the drifts from this model. This comes to the end of our tutorial, and if you find this tutorial useful, please do like and share, and if you have any doubts you can comment in our comment section, and for the upcoming tutorial videos please do subscribe to our channel.